Now we want to talk about the topic of acceleration. And acceleration has a similar meaning to velocity. Velocity is the change in position as a function of time or with respect to time. And acceleration is the change in velocity over the change in time. And this is also a vector quantity. So anytime you have a change in velocity, anytime you have a change in velocity, you're experiencing an acceleration. What are examples of acceleration? Well, if I let my pen fall, right, we all know that it is accelerating downward. It's gaining speed as it does so. That's one interpretation of acceleration. If you have motion along a straight line, if you're speeding up or slowing down, then you are accelerating. Another interpretation of acceleration is moving around a curved path. Because velocity is directionally dependent, if my direction is changing, my velocity is changing, and if I have a change in velocity, then I have an acceleration. So I can either speed up or slow down, or I can move around a curve, and all of those will produce an acceleration. Now, I can derive a formula for the final velocity of an object if I know its acceleration, its initial velocity, and the time interval over which the motion has been occurring. So if I solve this equation for VF, the steps are, I won't write them out explicitly, you guys are all good at math, but the steps are multiply both sides by delta t, and then add VI, and I get VF equals VI plus AT. Now, I want you to take a look at this formula really quickly. What is this allowing me to do? This is going to allow me to calculate the final velocity at the end of some acceleration if I know the initial velocity and if I know the acceleration and if I know the time. Now, there's one caveat here, and this formula is only strictly valid if the acceleration is constant. Okay? So this is valid if A is constant. But under that condition, if I know these three, I can calculate what my final velocity is. So if I know how the velocity is changing with respect to time, and I know what my initial velocity is of any object over any given time interval, I can predict then how fast the object is going to be moving as a result of that acceleration. Okay, that's the interpretation of this particular formula. This is also known as the average acceleration. Okay, that is also known as the average acceleration. Acceleration also has an instantaneous interpretation to it, and we write the instantaneous acceleration, again, just as A, but it is the first derivative of velocity with respect to time, but because velocity is the derivative of position, then acceleration is equal to the second derivative of position with respect to time. And so all of these definitions represent equivalent expressions, right? So the acceleration is equal to the first derivative of velocity with respect to time, or it's equal to the second derivative of position with respect to time. Now, from these equations, I can derive a set of formulas that are extremely useful that are known as the kinematic formulas, okay? And the kinematic formulas are going to allow me to solve a variety of motion problems, right, under constant acceleration. And so you've already seen one. We've already seen one. We derived it in the previous part. VF equals VI plus AT. This is the first of the kinematic formulas. Okay, and this allows you to find velocity if you're given acceleration, time, and an initial velocity. But what if I'm not given one of these? Let's say that, for instance, I want to find the displacement of an object as a function of initial velocity, acceleration, and time, but I don't care about my final velocity. Okay, how can I go about then determining the total distance? If I'm moving in a straight line, I can use distance and displacement interchangeably. How can I find the total displacement along a straight path if I don't care about the final velocity. So what we do is we start out with this definition of acceleration, and I'm going to drop the vector notation momentarily, and we say that, of course, acceleration is the derivative of velocity with respect to time. And what I can do is rearrange this formula for dv. If I rearrange it for dv, then this is going to give me a dt, and I can integrate both sides of my equation, and I'll integrate from my initial velocity to some final velocity, we'll just call it v, and I'm going to integrate from t equals 0 to some final time t. So I'm going to assume that my stopwatch almost all the time starts from 0. Right? So if I integrate dv, I'm just going to get v, and if I integrate a dt, I get a t from 0 to t, which is just at, and then I have this vi, so this technically is v minus vi, and I'm going to add my vi to the other side, and lo and behold, that's just the expression that we had before. V equals vi plus at, or v equals at plus vi. So this equation also falls out of the integration of the definition of acceleration, and vi you can now consider as a constant of integration. And now what I can do, and vi is a constant, okay, so when I integrate dv, or not dv, but dx dt, when I integrate that, this will remain a constant, okay? So we know that v is equal to dx dt, so now I insert that into here, and I multiply again both sides by dt, and that gives me dx is equal to at plus vi dt, and I integrate again, and I'm going to start my motion at my initial position, it will end at my final position, and I will start my stopwatch at 0 and go over the same time interval that I did before. Now, before we go any further, I should mention that we've now accomplished our goal. This expression is going to relate my displacement, xf minus xi, in relation to the variables I was interested, acceleration, time, and initial velocity, and now I don't have to know what my final velocity was. I now have a formula that's going to allow me to find the displacement of a object if I only have an acceleration, time, and an initial velocity. So if I integrate dx, of course I just get x, and I evaluate that at my endpoints. This is going to be xf minus xi, and that is going to be equal to, I integrate both of these terms, and if I integrate at with respect to dt, I'm going to get 1/2 at squared, and if I integrate vi, I'm going to get plus vit. And I would technically have to evaluate these between t and 0, but because I'm using 0 as my initial time value, t minus 0, all my 0 terms are going to drop out. So this is my final formula for the displacement. This is delta x, notice, okay? So this is delta x, and that equals 1/2 at squared plus vit. So now I have a formula that will allow me to relate the distance an object travels moving in a straight line under constant acceleration over some time interval and knowing what its initial velocity was. Another added bonus, very often our initial velocities are going to start from rest. And so then our displacement will just equal 1/2 at squared. So you'll want to box this equation and put it away somewhere, along with the vf equals vi plus at. You'll want to box that equation and put it away somewhere. But now what if I don't know my time interval, and all I'm given are my velocities, or I should say, what if I want to know my final velocity? I'm given an initial velocity, an acceleration, and a displacement. How can I predict what my final velocity will be? In this case, I don't know what time is going to be. So, to derive an expression that relates two velocities, acceleration and displacement, we start again with this expression. Acceleration is equal to dv dt. But now I multiply the right side of my equation by 1, but in the form of dx over dx. And because I now have two fractions, I can multiply in any order. I'm going to rearrange the denominator, and so my denominator is going to look like this. And so now we have dv dx, dx dt. But dx dt is just the instantaneous velocity. So I can replace dx dt with velocity. And if I now integrate this, what I need to do is multiply both sides by dx. And if I multiply both sides by dx, I'm going to switch everything around so I'll get my velocities on one side. I'm going to get v dv equals a dx. And now if I integrate from some initial velocity to some final velocity, and I integrate this side over my position interval, then what I'm going to get is the integral of v dv is 1/2 v squared from vi to vf, and this is going to be a times xf minus xi, but xf minus xi is just my displacement, so this is delta x. And so I can multiply now both sides by 1/2, or by 2 rather, and if I multiply both sides by 2, I get rid of my 1/2 here. And this gives me v squared evaluated at vf and vi equals 2a delta x. And so the left-hand side turns into vf squared minus vi squared equals 2a delta x. And the way this equation is typically written is going to be vf squared, I add vi to both sides. So this is going to be vi squared plus 2a delta x. And that equation is the third of the kinematic equations, okay? Vf squared equals vi plus 2a delta x. Now I have an equation that allows me to find the final velocity under constant acceleration if I know initial velocity and displacement, and now I don't have to care about the time. We are going to use these equations an awful lot, and in the next video we'll do some examples with them. Thanks.